Hello, everyone, and welcome to your 14th lecture for Earth Science. This is going to be on the Earth's ocean floors. So we're going to be taking a look at those very mysterious, very deep, dark parts of Earth that are actually in some places less well known than the surface of Mars or the surface of the Moon. So we're going to shed a little light on those today. And next time we're going to move on to ocean water. And that will complete our kind of week-long little stint into oceanography. Going to look at the oceans this week, and next week we're going to start going into kind of more hard rock stuff like earthquakes, volcanoes, plate tectonics. After that, got 2 weeks of that, and then we're going to start weather. I think we have about 2 weeks of weather. And we're going to end up finishing the class with astronomy and looking at the night sky. So that's gonna be kind of the outlook of this class over the next several weeks. But for now, I'm going to be focusing on the ocean floor, and I start with this really stunning, beautiful picture of the Aegean Sea, just between Italy and Greece. Satellite image. It's pretty cool. So I'm going to talk about the ocean floor today. We'll get right into it. So this is a picture. First of all, you should know a little something about the oceans in general, namely how many oceans do we have, and a little bit about how ocean water is distributed across the face of the Earth. So, we have 3 big oceans. Those are the Pacific, Atlantic, and Indian. Now, the Pacific Ocean is the largest and the deepest. Average depth of the oceans is about 4 kilometers, and this is a real-to-life color image of the oceans, so it hasn't been, photoshopped. The color hasn't been photoshopped or anything. This is just the actual color of the oceans, kind of superimposed over the Earth. Of course, the continents have been blanked out with gray, but that's the real different, color differences in the ocean on average. So it's pretty cool. Now, the Pacific Ocean is our largest ocean, and then we have the Atlantic and the Indian that are also quite large. We have these other 2 oceans that are less well known. We have the Arctic Ocean and the Southern Ocean in the in the south near Antarctica. Now, oceans cover 71% of Earth's surface, so you should definitely know that for the test. I will definitely be asking about that on the final exam, and you should know the 3 largest oceans as well for the final exam. We also have an unequal distribution between the north and the south. So if we draw the equator in here. I'm trying to draw the equator. It looks like I'm changing the slide instead. So if we draw in the equator about right there, the northern hemisphere here has more land, less ocean, has only 61% ocean. And the southern hemisphere down here has more ocean than land. It has about 81% ocean. Okay. So a little bit about the history of ocean exploration. So the first really big voyage to explore oceanography, explore the oceans and launch the whole discipline of oceanography, started in England with the HMS Challenger and the voyage of the HMS Challenger. It was a 3-year voyage between 1873 and 1876 on a sailing vessel. So it wasn't even at this time steam powered or anything else. It was really just a sailing ship. And the crew, the scientific crew of the HMS Challenger, all these gentlemen here, recorded a lot of various aspects of the ocean and wrote it up in a huge report. So the surface temperature was measured along with the salinity of the surface water. They also looked at the bottom of the ocean. They would dredge up rocks. So first of all, they would measure how deep the ocean is. That's called sounding. And then they would dredge up rocks from the bottom, rocks and sediment from the bottom, just to get a look at what is on the bottom of the ocean. They also collected a lot of biota, or a lot of life, living marine organisms. So this shows, the voyage of the HMS Challenger. Of course, it did a lot of loops around in the Atlantic, starting from England, and went all the way to Antarctica, right? Went to the South Pacific, through the Mariana Trench, across the Pacific Ocean, right? South America, through South America, right? So it was a very long, 3-year voyage. So they did, during that time, one of the things I find most amazing is they did a lot of what's called bathymetry. So that's measuring the depths of the ocean. And the way that they did it is kind of like probably the first thing you would think of when somebody asked you, how would you measure the depths of the ocean? That is, they took a really heavy weight, they put it on a rope, and they let it drop. And, it goes drop, 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 drop. So, however deep it is, they let it drop all the way to the bottom of the ocean. On average, it's 4 kilometers deep, So they must have brought 4 kilometers of rope. In other places, it's 36,000 feet deep, It's like they must have had miles and miles of rope. It's kind of amazing that they knew to bring that much rope, or they even had that much rope. But anyway, pretty amazing technique, and that's how they measured the depths of the ocean floor. Okay, so that's not how we do it today. We have kind of a little bit more sophisticated techniques. Nowadays, we use echo sounding to measure the depth of the ocean floor. So we have vehicles like this Chikuyu research vessel, sends out sonar pulses, basically acoustic pulses like sound waves, into the ocean. And just like, you ever play that game where you see a lightning flash, and then you count how many seconds it is between the lightning flash and hearing the thunder? Works a little bit the same way, right? It sends out an acoustic pulse. It's going to take some time for that acoustic pulse to hit the bottom of the ocean and bounce back as an echo. And from that time delay, we're going to figure out the depths of the ocean. Okay, so that's how they map out, That's how they make the best maps of the ocean, through sonar, echo sounding. It's called echo sounding. Another way that this is done is through satellite altimetry. So a satellite shoots a laser right here down to the surface of the water. Now that laser bounces back, and you get a height of the ocean floor. Sorry, not height of the ocean, sea level, the water level. Now, what's kind of interesting is that the water level, the actual water level, is affected by the depth of the ocean floor. So if the ocean floor is particularly deep in some place, the water level will actually be a little bit more popped up, and that is because there's missing mass because of the depth of the ocean in that particular place. Some mass is missing and does not exert the normal gravitational force on it. And so that kind of missing gravitational force from the missing mass of that hole in the seafloor results in the water actually being popped up a little bit, which these are very minor effects. They're maybe just millimeters, but the satellites are so precise they can actually pick up on those small variations and get an idea about what the ocean floor is like at those places. So we get a rougher image of the seafloor, not as detailed, through satellite altimetry. Sonar is the best way to map it out, but this is a much slower process than through satellites. Okay, we can also take submersibles down to make very detailed explorations of the seafloor, and we found some very interesting organisms and life forms that occur near the seafloor. For example, these things called black smokers are pretty cool. They're constantly belching out this. I'll show some videos of this in the next lecture. Constantly belching out this, basically mineral precipitates of iron sulfide that are black in color, and this has created a lot of really unique, the heat that's coming up from the seafloor. And a lot of these places are volcanic. Again, we'll cover this in the next lecture. Really creates a lot of interesting ecosystems on the seafloor that were very unexpected. We kind of thought that the seafloor would be sort of devoid of life in certain ways, but in certain places it is. There's no life on the bottom of the Mariana Trench, for instance. But it's kind of these are very interesting ecosystems that occur around hydrothermal vents on the seafloor. Okay, so the ocean floor. Here is kind of a general map of the ocean floor with this sort of exaggerated topography. You're going to see that we call this study of the ocean floor distributions at different elevations. We call this hypsometry. Now remember that on planet Earth we have two kinds of crust. We have continental crust and we have the ocean crust. Okay, Ocean crust is thinner and denser. Continental crust is less dense and also thicker. That results in the continents being kind of, elevated compared to the oceans that are sunk down low, sinking lower into the mantle. Okay. Remember, the mantle is not a liquid, so it's a solid. However, it's still kind of malleable enough to allow for a gravitational equilibrium. You might remember that term isostasy to take over, and so the thinner, more dense ocean crust sits lower than the continental crust, and that's why we have ocean basins to begin with. Okay, so you might notice some kind of interesting features here. We have these sort of popped up areas off the coastlines that are actually still areas of continental crust. So this kind of aqua blue turquoise color you see here, this is all continental crust that's just been flooded in with ocean water. So we call that area the continental shelf. And this, you notice there's also a kind of a large ridge or mountain range in the middle of the ocean. We call that those mid-ocean ridges. The one in the middle of the Atlantic is called the Mid-Atlantic Ridge. And you also notice that we have these very deep areas of the crust, ocean crust. Those are the abyssal plains. Okay. Now, you'll notice we have other things here as well. There, in some areas, like take Bermuda, for instance, we have parts of the ocean floor that are so elevated, kind of so popped up, they actually get above sea level. So these are volcanic islands that take place in the middle of the ocean. So those are called seamounts. You'll see we have a lot of seamounts that are actually below the surface, even though they are kind of elevated relative to the average topography of the ocean floor. Okay. So hypsometry is the study of distributions of elevation over the surface of a planet. The Earth has kind of an interesting hypsometry. It's actually very unique compared to the rest of the solar system. So most planets have just one peak in their distribution of different elevations, but the Earth has two. So you'll notice that we have two peaks here. One, two. One corresponds to ocean crust, the other to continental crust. Now you notice on the vertical axis, this is elevation. And on the x-axis here, we have percent of Earth's surface. Okay, so what this is saying is that there is, maybe going down here, maybe 20% of Earth's surface is around, this is maybe corresponds to, this would be one kilometer. This would probably be about half a kilometer, so 500 meters, right? So it's saying that about 20% of the surface is at about 500 meters, and that's about the average elevation of the continental crust. Okay. On the other hand, you can see that going like this, the average elevation, this is maybe like 4.5 kilometers, negative 4.5 kilometers. We have another peak which represents the ocean crust. So, the average depth of the ocean crust, again, it makes up about a little bit more, maybe 25% of the surface of the Earth, is at about negative 4.5 kilometers. Okay, so the reason that we have two peaks here on Earth in our hypsometry curves is because, and like I said, most planets don't have two peaks, they only have one peak. The reason that we have two peaks is because we have two types of crust. And what you'll learn coming up in next week is that the reason that we have two types of crust, continental and ocean, is because we have water on Earth. So a lot of those other planets don't have abundant water, and that's why they don't have ocean crust. Or sorry, that's why they don't have continental crust. They have actually something equivalent to ocean crust. So Venus, Mercury, Mars, they're covered basically with what we would call ocean crust. So it's pretty interesting that the only reason we have the continents is because of water. So water and the oceans came before the continents. Okay. Anyway, that's all kind of getting back into historical geology, so I'll move on here. Let's talk about kind of general shape of the ocean floor. So where plate tectonics, by the way, was discovered, I shouldn't say recall our lecture. I used to do plate tectonics before this lecture, so I should really erase that because we're going to get to seafloor spreading and plate tectonics next week. But Remember that we have three types. I already discussed these things, but we have three types of three provinces of the ocean floor. We have mid-ocean ridges. We have the abyssal plains that are on either side of the ridge, and we have continental shelves. There are also three other kind of smaller features of oceans that consist of ocean trenches, seamounts, and fractures. And we're going to talk about all these things in turn in our study of the ocean floor. So here you go. Continental margins or continental shelves are on the margins of the continents. Abyssal plains get into the deep parts of the ocean. And the abyssal plains are separated by spreading ridges. And which, on each side of the spreading ridge, you get abyssal plains. And of course, again, going back to the continents, you have continental margins. Okay, so those are the three big provinces that we have. And if we are going to take kind of a side-to-side view of the ocean, like a cross-sectional view, this would represent the continental margin. Over here, the continental margin. The deep areas are the abyssal plains, and the mid-ocean ridges are like this. They're popped up relative to the abyssal plains, maybe 2 to 3 kilometers high relative to the abyssal plains. So ocean crust is younger than the continental crust. Actually, it's only about 180 million years old at the oldest, which is less than 4% of Earth's age, right? Earth is 4.5 billion years old. Okay, 180 million years is nothing compared to 4.5 billion. So ocean crust is younger than the continental crust. Continental crust is quite a bit older. So one thing that you notice about these ridges, and we're going to get into this in great detail as we go study plate tectonics next week. Well, one thing I want to introduce now is that if you look at the age of the ridges, the age of the crust at the ridges, here's the Mid-Atlantic Ridge right here, right? It's very, very young. It's just like maybe 1,000 years old, okay? Maybe just hundreds of years old. So this is all new baby crust that is forming at the mid-ocean ridges, and it gets progressively older as you move away from the ridge. So as you get further and further away from ridges, the ocean crust gets older and older and older. Okay, so the oldest crust is here, round off the coast of off the east coast. And also, by the way, here in the Caspian Sea, there's also some extremely old crust as well. Anyway, the Caspian Sea is very, very interesting because it's like not quite ocean water, but it's not quite fresh, and the depth of it is actually more like the ocean and there's actually ocean crust on the bottom of it. So it's actually kind of interesting. It's a closed up. It used to be an entire. It's crazy in a way, but the Caspian Sea used to be a whole ocean called the Tethys, and it closed up, during the last eon, in the Phanerozoic, it closed up. It's a very, very ancient ocean, and some of the oldest seafloors there too. So anyway, that's a whole nother story. But we're going to talk more about all that stuff come next lecture, or not next lecture, the next week with plate tectonics. So there are two types of continental margins, by the way. We have two types. So, continental shelves, continental margins. We have what's called a passive margin, okay, a passive margin, and we have an active margin, okay. A passive margin is where we have no plate tectonics taking place. So there's no earthquakes, no volcanoes, nothing exciting happening. That's like the east coast of our country. On the west coast of our country, on the other hand, is an active margin where you have active subduction, you have plate tectonics taking place, you have trenches, and you typically have a much shorter continental shelf as well. So just kind of want you to be aware of those two distinctions in the kinds of shelves. A lot of this stuff, I'm going to make it more clear when we talk about plate tectonics. I'm just sort of introducing some of the concepts to you. So if you take a look at passive margins, the whole east coast of our country is a passive margin. There's an active margin down here in the Caribbean, and again a passive margin along the east coast of South America. All of Europe and Africa is, or I should say the western edge of Europe and Africa is all a passive margin. Okay, but on our west coast, so California, Oregon, Washington, that's an active margin. That's why there's a lot of earthquakes, a lot of volcanoes out in that direction. Think of Mount St. Helens, for instance, right? So let's talk about passive margins now. So passive margins typically have much broader, wider, bigger continental shelves, which is the edge of the continents. Okay, so these things are very built up. This is a picture of the LA Basin and the continental shelf off the LA Basin. So the continental shelf is where you have shallow water that's underlain by a continental crust. Okay, so what's actually under here is continental crust. These are important economic deposits of oil and also very important commercial fishing grounds. Okay, you'll notice these deep cuts into the shelf. These are called submarine canyons. So these are areas where there is maybe a river. So probably there's a river flowing in here. I don't know exactly which river it is. It might be the Santa Ana River. It might be the Los Angeles River. I'm not exactly sure which one it is. But these rivers are flowing out from the continental crust into the ocean. It's cutting these very deep canyons into the continental shelves. Okay. So continental shelves have very low gradients. That means they get deep very slowly, only about 1% gradient. So that means that if you go out into the water, you have to go out about, on average, maybe 100 feet to go down 1 foot. And you have to go out another 100 feet to get down to get down 2 feet. So that's the average gradient over the continental shelves. Okay. Now the continental slope is right here. Okay, I'm going to draw kind of around the edges of the continental slopes. Okay. Oh, it's a submarine canyon there. Okay, so this area here between the red lines, that's the continental slope. Okay. So the continental slope is basically this area where it's very steep, has between a 5 and 25% gradient. That's very steep. So that means if you go out, for example, 4 feet, you're going to drop down 1 foot. Okay, so it gets deep very, very fast. And at the bottom of the slope, that's when you get into the abyssal plains and you get into the actual seafloor. Okay, so it's basically represents the end of the continental crust and the beginning of the ocean crust. The last thing is the continental rise. So the continental rise is this kind of shallower area, kind of like this. It's not as steep. This doesn't have as much of a continental rise here, but you see it really well right here between the red lines. Okay, so it's all this area right in here. So the continental rise is where a lot of sediment has eroded off of the continental shelves, and it's at the base and kind of forms a fan, a big large fan of sediment at the base of the shelf. And it's got kind of a more shallow slope. Okay, so it has a shallower slope, maybe more like a 5% gradient, and it sits right at the base of the shelf. Okay, so you also have these things, like I pointed out, submarine canyons, where you have rivers from the continents flowing into here, and it's opening up a large canyon, eroding through the continental crust. Now, you might wonder, like, why don't you have these big valleys here in the continental? Like, look at it, like what a huge canyon this is, carved into the ocean floor, right? The ocean crust. Like, why don't you have that up here on the continents? And the reason is that because there's lots of erosion taking place over the continents here, and it's eroded the topography on either side down. So you don't have that in the oceans. Okay, you don't have that active erosion of wind and rain constantly lowering the topography and eroding the topography away. Okay, so anyway, submarine canyons are carved out by something called turbidity currents. These are the currents that are coming off of the rivers from the continents that are laden. They're very dense waters laden with sediments, laden with kind of dissolved contents that are very good and very erosive, very good at eroding the bottom of the continental shelves. So these are collections of sediment at the termination of the submarine canyon, form abyssal fans that eventually expand and merge together along the margin of the continent to form the continental rise. Okay, so you can see at the base of the submarine canyon, you get these big piles of sediment, almost like deltas. You know, like you can imagine a big deltas that form at the mouth of rivers, right? So you get kind of things like submarine deltas that are called submarine fans. Okay, so I don't know why I always have such trouble getting these things to play. I had a video here. I don't know why it doesn't play. So here, hold on one second. I'm going to pause this. I'm going to go find this video so I can play it for you. Okay, so I'm going to play this video. I found it on YouTube, so I'm just going to play it for you here.
Experiment. In this experiment, researchers use a sandbox submerged.
So they're just going to show you kind of a simulation of how submarine canyons form. Okay, so I'm going to play it now.
In water to simulate how ocean currents carve underwater canyons. They pour a stream of heavy salt water over the sand in 10 stages and lower a downstream barrier for each stage. Canyons start to appear after about 30 minutes. The canyons get deeper over time, and about halfway through, ridges begin to develop. The canyons start to build their own drainage networks as the experiment goes on. As the 3 largest canyons in the center redirect the flow of water, those on the outer edges of the box disappear. The experiment shows that submarine canyons are self-similar. This means the entire canyon structure has the same shape as its parts.
Okay. We'll go back to the lecture here. So let me get rid of this thing. Okay, so let's take a look at this now and see if you all can figure out where's the shelf, where's the slope, and where's the rise. So this is off the coast of, you can see, New Jersey and Long Island. So first of all, where's the shelf? So the shelf is all this area, right? All this kind of aquamarine, turquoise area that you see here. That all represents the shelf, okay? Now you can see that there's obviously a submarine canyon here. That might be the Hudson River actually emptying out into this bay and creating this submarine canyon. So you can all see that pretty clearly, I hope. So I'm going to put sub-canyon here. This is going to be shelf. Now there's the slope. So here's the slope, right? This is where it gets deep very fast. So you can maybe see it here. I'm going to write here slope. And you can see kind of just the hint of a rise down here where the gradient is not as steep kind of at the bottom. So if you were looking at this in a cross-sectional view, it'd be like here's the continent, goes down into the shelf, then the slope, and then here's the rise, and then there's the ocean bottom. Okay, and then I'll draw on the water level would be like this, you know. Okay, so this would be shelf, slope, and rise. Okay, and then this would be the floor, the abyssal. Actually, I should call this the abyssal plane. Okay, so that's how it goes. So there's the rise. Okay, so now let's talk a little bit about active margins. So this is where active plate tectonics is taking place. I understand I haven't talked about plate tectonics with you yet, but just kind of, like I said, I want to introduce the idea to you before I get into it in great detail next week. So subduction zones occur along these active margins. And subduction zones are when the lithosphere is going to subduct back into the mantle. It's basically where the lithosphere is recycled back into the mantle. So you get these areas where lithosphere is sinking back into the asthenosphere below a chunk of the continental crust. Okay, so here along these margins you get deep ocean trenches, and you get a lot of volcanoes, a lot of earthquakes around this area as well. So this is a map of the whole Earth showing in red where active margins are and showing in blue where passive margins are. So you can see that the Pacific Ocean is actually basically covered in active margins, and we call that the ring of fire around here. This is the ring of fire, and the reason that we call it that is because there's a lot of volcanoes along these active margins. Okay, so isn't that sad? That doesn't show. Okay, let me pause this again and get this video. I don't know why it's having such trouble playing this stuff here. I'm gonna pause. Okay, so I found the video. So it's this just kind of shows you a little bit how active margins, kind of what goes on at active margins. It's a pretty good summary video put out by IRS, which is, gosh, what is it, like International Research something seismicity. But it's a really solid place to get good information about anything related to seismology. So anyway, this video is just going to kind of outline for you with a simple animation what goes on at a subduction zone, what goes on at these active margins. Okay, so without further ado, I'll play it for you.
In a subduction zone, the thinner yet denser oceanic plate dives beneath the continental plate. The continental plate is locked to the subducting plate by immense friction along the shallow portion of a vast sloping fault surface. GPS data from many subduction zones show that the friction indeed causes the leading edge of the overlying plate to be forced backwards. During subduction, the thin layer on top of the oceanic plate is scraped off and forms a wedge at the front of the continental plate. The continental plate deforms in response to the stress. The plates can lock for hundreds of years until frictional stress is overcome in a process called elastic rebound. This can produce magnitude 8 to magnitude 9 great earthquakes. Tsunamis occur when the ground beneath the ocean is displaced, as it does in this simplified animation. This cycle of locking and building stress, followed by catastrophic release, repeats every few hundred years.
Okay. We'll stop it there. Go back. So over millions of years, the ocean floor accumulates these sediments, and those sediments are scraped off, and they accumulate in these accretionary wedges. So that video showed that pretty well. So trenches also form along active margins. These are the deepest parts of the ocean. They occur where subducting plates start to sink into the asthenosphere. So this is the deepest point on Earth, was measured by the Challenger voyage, Challenger Deep in the Mariana Trench. So there's Challenger Deep. It's in the Mariana Trench, which is off the coast of Guam, pretty close to the Japanese islands and South Pacific islands. So anyway, this is where, you know, basically the ocean crust is literally sinking back into the mantle, so you could imagine how this could be very, very deep. This is another video I wanted to show you about James Cameron visits Challenger Deep. So it was kind of funny. James Cameron did this video, and he goes down to Challenger Deep in a submersible, you know, but it's kind of actually a boring video. I only show the trailer for it because the video itself is sort of boring because there's really nothing there. You know, like there's no life. There's no like weird crabs or something at the bottom of Challenger Deep. You know, it's just mud. So nothing can live at that pressure. So anyway, I'm going to go find that video again. Sorry for the inconvenience of having to pause this all the time. Okay, so I found this video again. And yeah, it's funny looking through all these videos. James Cameron did this. He went down Challenger Deep in a submersible. And there's all these interviews with him. And you watch the interviews and it's like he doesn't really even have anything to say because you go down there, you can watch the video, you know, and he moves the camera around, and what's at the bottom of the Mariana Trench? Nothing. There's just mud. You know, it's not very interesting. But I thought the trailer for it was pretty cool, so I've got to play the trailer for you. So. Yeah, the simple reason is there's nothing to see down there. But it is, I like this animation because it gives you an idea about just how deep it is. It's pretty crazy. So here's going to Mariana Trench. See, it's crazy. We get to 12,000 feet, and we're only, it's where the Titanic's resting place is, which is the average depth of the ocean, by the way. And we're not even, we're not even 1/3 of the way there. We're not halfway there. So it keeps going down. It's 3 times deeper than, however deep the Titanic is. So. Yeah, so this is the snailfish. This is the deepest living fish ever found, and it's only at 25,000 feet. So it's crazy. It's like that's the very deepest anything can live, 25,000 feet. I don't think there's any signs of life once you get beyond this, and then it still goes down another more than 10,000 feet. And then he's showing you here. You're actually going deeper than the Mount Everest is tall. And they actually kind of even make the bottom of this look more interesting than it really is, because when you actually look at the real video, he gets down there and it's perfectly flat down there because it's just sediment. It's all filled with mud. It's pretty boring. So anyway, I've made my point. But let me get back to the lecture. So anyway, what's up with Bermuda? I show it's kind of popped up in the middle of the abyssal plains. So, Bermuda's a volcanic island that sometimes you get these random volcanoes that happen in the middle of the ocean crust. It actually has to do with impurities found in the mantle that cause a lot of flux melting and volcanism there. But anyway, that's why we have these kind of random places, seemingly random places in the middle of the ocean that are popped up like that. Okay. The abyssal plains are vast areas of the ocean floor. Most of the ocean floor is abyssal plain, and it is totally covered with sediment. There's lots and lots of sediment, hundreds of meters, some places kilometers of sediment covering the volcanic rocks below. So these are very, very flat areas. In fact, these places are so flat that you could go 1,000 miles in every direction and not find anything higher than maybe 9 feet. Okay, so it's extremely flat. It makes the Great Plains, like parts of, America, like the Great Plains that are very flat, makes it look like, mountainous, really, compared to how flat it is on the bottom of the abyssal plains. Okay, so so now I've talked about abyssal plains. I've talked about continental shelves. I am going to talk about a little bit about mid-ocean ridges. I think maybe I did talk a little bit about them already. I don't think did I talk about mid-ocean ridges? Oh yeah, I do. I do eventually. I get to mid-ocean ridges later, but I do kind of want to talk about just other kind of random things that are out in the middle of the seafloor. So we have things called fractures. You can see fractures here. These are kind of deep cracks in the crust, ocean crust, that form with plate tectonics and the shifting and spreading of the seafloor. So we'll talk about those more another time. We have hotspot tracks. I'll talk about those more a little bit. We have seamounts. Seamounts are basically submarine islands. They're islands that they're popped up, but they don't quite make it above the surface. Okay, so we'll talk more about those. Let's talk about the Hawaiian hotspot track. So it's pretty cool. So you can see this is Hawaii right here. Okay, those are the Hawaiian Islands. Now, what's pretty cool is that there are a few islands there, right? And as you go from right to left, or I guess if you go from east to west, the islands get smaller and smaller and smaller. And actually, there's a whole track of islands that are there below the surface. And they go all the way here, all the way tracking. Let me get different colors so you can see this. They go all the way tracking from Hawaii to the Aleutian Islands off the coast of Alaska and off the coast of Kamchatka and Korea and Siberia, or not Korea, Kamchatka, it's right there. That's in Siberia. So it's pretty crazy, but there's a whole long line of submarine islands which represent old Hawaiian islands going all the way to Siberia. Isn't that crazy? It's true, though. So what this actually is doing is the plate is moving. The Pacific plate is moving. It's shifting. We're going to study this more when we talk about plate tectonics. And below Hawaii, there's a stationary mantle plume. That mantle plume is causing all the volcanism that generates the Hawaiian Islands. Now, as we move over that mantle plume, as the plates move over it, it keeps generating new islands. But as those islands go on with time and they move off of the plume, volcanism stops. They stop kind of building up, and they end up eroding away, and so they get smaller and smaller and smaller. So you can see that the big island, Mauna Loa, is bigger than Maui, bigger than Molokai, bigger than Oahu, and they get smaller and smaller as you move from the east to the west. And that's because they keep eroding down because volcanism has ceased after it moved off of the hot spot. And you can see very clearly, you can actually go and date all these seamounts, right? Hawaiian Islands are brand new, like 0 years old. And they get subsequently older and older, right? So Maui is 1.3 million years old. Molokai is 1.8 million years old. Oahu is 3.4 million years old. So they keep getting older all the way to 64 million years ago, and in which they're kind of linking up with the Aleutian Islands and Kamchatka and Siberia. So it's pretty crazy when you think about it that way. So let me play yet another video for you, kind of show how this process goes. So these are, again, hotspot track volcanoes. Okay, I found it. So here's the video. I'll just play it for you. Another one by Iris. This is on hotspot tracks.
A hotspot is a localized source of high heat energy that sustains volcanism. It is not an isolated shallow magma reservoir beneath the crust, nor is it a pipe of magma that streams from the outer core. One theory holds that hotspots may begin as a blowtorch-like thermal perturbation in a zone between the liquid outer core and overlying mantle about 2,900 kilometers deep. The thermal plume allows solid, yet mobile mantle to rise very slowly and convect outward. Convection is the process by which heated material rises and cooler material sinks. Although magma may be generated as deep as 1,500 kilometers, individual blobs do not traverse the entire mantle. Let's zoom in to look at the onset of hotspot volcanism beneath a moving plate. As each pocket of melt stalls, its heat is transferred to adjacent rock. This transfer continues to the base of the tectonic plate, where decreased pressure facilitates rock melting. The magma that forms at the base of this plate rises through the plate in a network of cracks and shallow chambers and erupts on the surface. Over hundreds of thousands of years, large volcanoes build on top of the plate. The weight of the volcanoes bends the plate downward. Volcanoes that spent their constructive life over the thermal plume slowly get rafted away on the moving plate, and new volcanoes build in their place. Multiple dikes can feed several volcanoes from separate conduits. The moving plate drags the thermal plume with it. This can explain why volcanoes can erupt again after centuries of quiescence, even after they have moved off the center of the hotspot. However, erosion greatly outpaces volcanism as eruptions wane, and the buoyant effect of the plume diminishes, allowing the volcano to subside.
So once the volcano subsides and erodes, it sinks back under the ocean floor, and it becomes, or ocean sea level, and it becomes a seamount. Okay, so I'll move back to the lecture here. So as the volcanic island, as volcanism ceases, Also, by the way, you often have these coral reefs that are building up off of the sides of the volcano. So the coral reefs are building up and building up. Now the volcano will go extinct and it'll start to erode away. And pretty soon you have a seamount, or what's called a guyot. If it's flat-topped, we call it a guyot. And at the same time, you'll have these coral reefs that are still building up and building up and building up and maintaining themselves because they're made out of living organisms, right? So, corals are living organisms. They build up their skeletons out of calcium carbonate, and they build themselves up this way. And so if you look down, a lot of times you'll end up with these things called an atoll. Okay, so you'll have a barrier reef that surrounds a volcanic island. And then eventually the volcano, after it dies, it will just erode away. And you have what's left is just this random kind of ring of coral reef in the middle of the ocean called an atoll. Okay. When you get these flat-topped, basically volcanoes that have been eroded by wind and rain and wave action, it erodes them away. They go below the surface. You get these flat-topped kind of tabletop seamounts. Those are called guyot. So yeah, there you go. That's how you go from a volcanic island, how it eventually turns from volcanic island, active volcanic island, to a sinking island, to a guyot, to ultimately an atoll, and ultimately a seamount. Okay, so that's a pretty good kind of side view of how that process goes. Other features are things like oceanic plateaus. We have one very significant oceanic plateau, which is just an area that, by all accounts, should be deep because it's overlying ocean crust. However, it's overlying the abyssal plains. But however, they're popped up basically because there's been huge amounts of volcanism. So one very good example of that is the Ontong Java Plateau, which is off the coast of Papua New Guinea here. And these are huge areas of elevated topography on the ocean that formed through intense periods of hotspot volcanism. Ontong Java was really amazing. It was 30 kilometers thick outpouring of hotspot basaltic lava 120 million years ago. I mean, it's like, imagine all of the volcanism from Hawaii ejected over a period of maybe like 1 million years. So, Hawaii's been going for 64 million years, right? So it's just tremendous outpouring of lava. Some of these huge outpourings of lava are thought to be connected with mass extinctions, and whether mass extinctions 120 million years ago, I think there was around that time. So that would have been between like the Cretaceous and Jurassic. So anyway. Let's move on to ocean ridges. So these are the longest topographic features on Earth. Okay, these are actually the longest mountains on Earth, mountain ridges on Earth. So where's the word? Mountain range is what I'm looking for. So they're pretty amazing features. They're 2 to 3 kilometers high, which is like 10,000 feet high, and they go for just thousands, tens of thousands of miles long. So, look at the Mid-Atlantic Ridge. Here's the Mid-Atlantic Ridge. Goes all the way here, further north than Iceland. There's Iceland right there. Goes all the way down here, almost to Antarctica. Almost like goes, circumvents the world, or at least goes halfway around the world, from North Pole to the South Pole. They're really amazing, and they're so very long mountain chains that are all underwater. And these are created by the process of seafloor spreading, where the ocean floor is expanding. There's active volcanism, and these things are creating these very high mountains, volcanic mountains. Okay, so you have the Mid-Atlantic Ridge here in the middle of the Atlantic. You have in the middle of the Pacific, the East Pacific Rise. This is a very fast, very powerful set of volcanoes here in the East Pacific Rise. They erupt a lot of material. Then you have the Southeast Indian Ridge there below, south of Australia, and you have the Mid-Indian Ridge. And that's in the middle of the Indian Ocean, and the Southwest Indian Ridge. So what's this one? The Chile Rise right there. Okay. So anyway, those are the major rises, mid-ocean ridges in the ocean. But the most important ones are the MAR, the Mid-Atlantic Ridge, the EPR, the East Pacific Rise, and the Mid-Indian Ridge. Okay. So rift valleys form in the middle of these spreading ridges, so they're very similar to continental rifts. So if you look at these ridges, they'll look like going up from the abyssal plains. They'll start to rise like this, and right in the middle there'll be a trench kind of like that, and they'll go down to the abyssal plain. So these are like rift valleys, or that form right in the middle of the trenches. Okay. So that's basically the biggest provinces of the oceans I've talked about now. I'm going to finish up here just a few words on sediment. So, the ocean floor is totally covered with sediment, and you only need to go out to the bay, Corpus Christi Bay or Ozo Bay or wherever to realize that, right? You go out into the bay, it's covered with sand, rocks, mud, whatever it is. So the ocean floor is covered with sediment. Near shore, you're going to be depositing kind of coarser sediments like rocks, sand and cobbles, pebbles, things like that. But as you go further out, you're going to get finer and finer and finer sediment. Okay, so the sources of sediment in the oceans are turbidity currents. So that's remember, turbidity currents are the rivers that are flowing off the continents, bringing in sediment from the continents, eroded from the continents. Also, sediment that slowly settles to the bottom from above. So you can imagine all of the microorganisms that die in the ocean, all of the fish, all the organisms that are living in the water column above. Their bodies, they die and they sink to the bottom, and a lot of that is actually microorganic life. The vast majority of that material is microorganic, so you don't even see it. Okay. But once it accumulates, very slowly, probably every year it's about 1 millimeter of material accumulates from above. You also get wind-blown dust from the continents. Okay, so as you move away from the coastal areas, the sediment is going to get finer and finer and finer. So once you get into the abyssal plains, you don't find sand anymore. There's not going to be sand and cobbles and pebbles. It's going to be very fine mud and clay. So in the Pacific Ocean, you have about 600 meters of mud building up on the bottom of the ocean. Atlantic Ocean can be anywhere from 500 to 1,000 meters thick with this stuff. Okay, so we have also different types of sediment. We classify it either as terrigenous or biogenous. Terrigenous sediment, terra means earth. So terrigenous, genus means origin. So earth origin sediment. So this is sediment that's coming from the continent. So this is material weathered off the continental rocks. Virtually every part receives some of this. Fine particles remain suspended for a long time, and they go far out to sea, and they settle in the middle of the ocean. So another source is what's called biogenous. Biogenous consists of all of the living organisms that die, and they have bio, right, life, genus, origin, so life origin sediments. This is shells, skeletons of marine animals and plants. Most of these are calcareous, kind of like calcite-like carbonate oozes that form from microscopic organisms that inhabit warm water surfaces. So, the water is just filled with plankton. There's a lot of different types of plankton. There's things called radiolarians. I can write that out for you, radiolarians. Other forms are called coccoliths or coccolithophores, dinoflagellates. These are all different types of planktonic organisms that are microscopic, and they have little shells, what are called little tests. And those tests, when they die, they sink to the bottom of the water. And a lot of those tests are made out of calcite, which is a carbonate mineral. A lot of them are made out of silica, which is a silicate mineral. So for example, diatoms and radiolarians make their skeletons out of silica, whereas coccolithophores make them out of calcite. Okay. Also, phosphate-rich material from fish, from their bones and their scales and things also build up on the ocean floor through biogenous sediments. Okay, so these seafloor sediments can be very, very thick. We can actually measure the thickness of them through seismograms, through seismic reflections from echo sounding. We can actually get an idea of how thick these sediments are. This shows a kind of global distribution of different types of sediment. The red is terrigenous, and the yellow is kind of wind. So you can think of terrigenous as this is like turbidity currents. So stuff brought in from runoff from the continents. Clay you can think of as the wind-blown. Wind-blown kind of terrigenous sediments. Siliceous ooze is biogenous. And carbonate is also biogenous. So you can see that places where you see green and blue, it's dominated by biogenous sediments. Places that are red and yellow are kind of dominated by terrigenous sediments. You can see that it makes sense that if you surrounding the continents, it's mostly terrigenous sediment. Notice also something here in the poles, the North Pole, it's almost all terrigenous sediment. And why is that? It's mostly all terrigenous sediment because there's very little life in the water column there. It's too cold. So there's very little biogenous sediment. It's mostly terrigenous. Okay, so that's all I have for you today. Hope you enjoyed the lecture, and I will talk to you next time about ocean water. So till then, have a good day.